The definition of work in terms of our everyday use of that word is fairly different from the way it is done in physics. In everyday work, we can be sitting on our desk and doing some written work, and we call that as doing work. The work is completed, not completed. I did a lot of work today. I couldn't do so much work today. We get a sense of what is work. When parents come back from office and they say that today there was a lot of work, I got very tired. They may have just sat in the office all day in front of a computer, or maybe called people and spoke to them the whole day. They'd get pretty tired, but that does not mean in terms of a significant amount of work was done. In physics, we have a very specific definition of what is work. We say that work is done if and only if, and I don't know if you know this from mathematics, IFF. Do you know that from mathematics? If and only if. Okay. So in physics, we say that work is done if and only if a force is applied on an object, and when the force is being applied on the object gets displaced by a certain distance d. So it's obvious that it is the force that is causing the object to move, and therefore we say work is done. Specifically, work can be calculated when you find out the product of the force and the distance moved by the object in the direction of the force. Okay, for the time being, I'm just going to put it like that, in the direction of the force. There's nothing strange about it. You apply a force in this direction. If that is the net force, that is there are no other forces acting on it, then obviously the object is has or can get displaced in this direction. But the displacement and the force are being applied in the same direction. Perhaps I can change this and make it like this, so that it's clear that it is going from this side to that side. Now, is there any question first of all? Anybody would like any clarification? Perhaps the next thing that we can look at then is what would be the unit for work done. Okay, what is the unit for work? From dimensional analysis, from looking at the units, force times displacement. Force is measured in newtons, right? And displacement will be measured in meters. This is of course for SI, and therefore work is measured in Newton meter. And we came across this same unit, the Newton meter, a little while ago when we were talking about moments of a force. Moment of a force is also measured in terms of Newton meter. Okay, so there is a certain there is a commonality between these two things, and in discussing it, we will bring that about, what that commonality is. Now, Newton itself is a composite unit, right? It is a unit, it's not a primary unit, it is a unit that is made up of other things. So you can rework this again. Newton is written in terms of kilogram meters per second square, because force is equal to mass times acceleration. So mass times acceleration times meter. So that could also be one way in which you write down the unit of work, but then nobody ever writes it like that. I'm just putting it out there because there is a possibility to do that over here. So this unit is not very significant at the moment. We will come back to it a little later when we look at work energy equivalence, or the concept of work and energy. Now, is there any question at this point of time? Now, there are obviously some consequences to defining work like that. You can apply a tremendous amount of force on an object. Like, say for example, there is some kind of a rigid object maybe a wall, and somebody could be doing some really hard work pushing against that wall. Okay, this looks like he's kind of flying, not flying, he's pushing against, he or she. So a force is being applied by this person on the wall, okay, and it is not to be confused with the fact that the person will eventually get tired, because you are using your musculature, you are burning your energy, you are converting, ATP, and so the Krebs process is going on. All that is happening, and you will get tired, you will sweat, your muscles will hurt, you may collapse. If you do it for long enough, you may get so tired you might collapse. But unfortunately, physics being what it is, it will say, well, let's look if work is being done. Is there a force? Yes. Is there a displacement? No. So we say that there is no work done. Therefore, work done is equal to 0 Newton meter. Okay. So the spending of energy, the expenditure of energy is not to be confused with work. Okay. When we say work is done, that means a force has to be applied and the object has to get displaced in the direction of the force. Okay. Otherwise, no work is done. Perhaps it is useful to say no work is done on the object. So we can say no work is done on the object. That means on the wall. There is nothing that has been done to the wall. The wall has not moved 1 millimeter from its original position. So therefore, no work has been done. So that is the argument that we use. Incidentally, I just like to point out, I just glanced into the textbook. In the textbook, the unit for, the symbol for displacement is given as S, and that is actually the correct classical use of the variable. So please use S everywhere that you see D in this derivation. But other than that, it's exactly the same. Okay, so this is as far as when forces are applied and the displacement occurs in the same direction. But that, of course, need not always be the case. It is possible that a force is applied in a direction which is not in the direction of the displacement. Like, say for example, a child is playing with a toy. So she's got a string attached to the toy and she is pulling the toy. Now, let us say that the toy gets displaced by a certain distance. Okay. Now the question is, what about the work done in this case? I'm just going to start using S so that there is no discrepancy between these two things. What is the work done in this case? Okay. And first of all, let us just identify where is the force. How will you show the force acting on the object? Think about the object, okay, not the person. How is the force acting on the object? So yes, as people have indicated, it is the tension along the rope that is causing the object to move. And what is interesting to note, however, is that that tension is not in the direction in which the object is being displaced. Okay, this line came out a little crooked, so I'm going to draw it parallel to the ground again, just so there is no confusion about it. Okay, again it came out crooked. Okay, it's fine. It's parallel to the ground, it's moving in this direction. So now over here, there is a slight problem, because earlier we had defined work in terms of force multiplied by displacement, and we also said that the displacement has to be in the direction in which the force acts. But obviously that is not the case over here. The displacement is at an angle to which the force is acting, or you can put it the other way around. The force is not causing displacement in that direction, it's causing displacement in this direction. So then how do we calculate the amount of work that has been done? Do we simply say, yeah, it is still force multiplied by the distance that is moved? And if you say no, then you have to say why not? And if you say yes, then somebody has to say why that would not be the right way of doing it. So if you just calculate T multiplied by S, what is the harm in that? What goes wrong? So can somebody answer that question? I'm going to keep that part of it still over here. And I'm just going to write for this situation. Can I still say work is equal to the tension, which is a force, multiplied by the displacement? Why can't I say that? What would be wrong if I did that? Because that's obviously going to give an answer. I give you some numbers for what is the tension and what is the displacement. You can calculate it, the answer will pop out in terms of Newton meter. If that is correct, then somebody has to say why it is not correct. And if somebody says, no, that's not wrong, that's not correct, it's wrong, why is it not wrong? What is your logical argument? That's what I want to hear. Of situation. I'll just present a couple of situations for you to kind of think about this. Like, we often use the idea of take it to the absurd, take it to the extremes, and then see what happens. Okay, so in that spirit, I'll put out two obviously extreme situations, and then tell me if they are both the same or not. One is when the force is being applied in this direction. Okay, so the tension is acting in this direction, and the other extreme is when the force is being applied perpendicular to that direction, which is that the tension is being applied in this direction. Okay, and obviously this situation is somewhere intermediate between this and this. So what you have to answer is whether this situation and this situation are the same, and if it is not the same, then how does it change? Okay, and we are talking about it in terms of the displacement. You can obviously see that the two situations are not the same, but I'm talking in terms of lateral displacement. I'm talking about it in displacement in the horizontal line. So is there a difference between these two? Yes, Rudra, the forces has to be external. Internal forces, like we have seen in class 8, internal forces do not cause any change in the momentum of the object. So internal forces will not be able to create any kind of displacement. So the forces that we are discussing is completely external. Obviously, as people are pointing out, the effect on the displacement between this point, sorry, not this point, but this way of applying the force and this way of applying the force are completely different. So in this case, you can see that this force, even if it is sufficient to move the object, it's only going to cause a movement in the vertical direction, in the y-axis. And what I asked was, what about the x-axis? So this is obviously going to produce zero change in terms of displacement in the x-axis. And therefore, if this is 0 and this is, I do not know, let's say for the time being maximum, because W multiplied by F times S, if the force is being applied in this direction and the displacement is in this direction, then if that is the maximum and this is the minimum, then obviously this has to be somewhere between these two extremes. Correct? And the factor that decides this, of course, is the angle. So if I just draw the vertical and the horizontal over here, so this is the x-axis and this is the y-axis, then there is an angle theta over here, okay, and that angle and its trigonometric function, we have to see which function it is. It could be cos or it could be sine. Usually it's one of these two, not tan, in mechanics cases. Then some function should decide what part of the tension is the one that is responsible for causing the displacement. Okay. So I'll just change the diagram a little bit so that you can see that section of it more clearly, and then maybe you will get it. There is one rule we are looking at that we have studied in class 8, which applies over here. So think about that. I'll just draw the other diagram. Okay, so over here then we show the tension which is acting at an angle, and then we have the two axes, the x-axis and the y-axis. We are interested in the displacement of the object in the x-axis, not in the y-axis. So what we are trying to find out now is that which part of this force, the tension force, is the one that is responsible for moving this object in that direction, right? So again, we fall back on the first law and the second law, which is that if an object has to change its state of motion, then a force has to act on that object, right? So there is a rule that helps us to split up vector quantities into their the constituent parts when we choose a certain axis. And we have chosen the axis over here, the x and the y. We are interested in the x-axis, we are not interested in the y-axis, because the y-axis part is when the object moves in that direction. That's not of concern to us at the moment. We are concerned about the movement in the x-axis. So what is that rule? Could somebody just say it?
Parallelogram.
Boo, man. Quick. Somebody just say it. It's all there.
Parallelogram rule.
What helps us split vectors? Okay, there now I've almost said it all.
So can you not hear us?
Nothing yet. All quiet on the Western Front.
I don't think you have.
Okay, send it in chat now if you don't want to speak. Oh, you're speaking and I can't hear you? Oh.
Yeah. Sir, it's already been sent on the chat.
The volume is up. Aha. So yes, the rule that we apply is what is known as the parallelogram law, where force being a vector can be seen as being constituent of two different vectors, and the vector addition of those two forces can produce a resultant force. We also learned the reverse of it, where we can use the resultant force and then break it up into its constituent components based on what we are interested in. So if you do that now, you see that you drop a perpendicular in these two directions, and then you break up the vector into two parts. One is this one and one is this one. Okay, so these two forces add up to produce the force T, and obviously this force is the one that we are interested in. Okay, and that force, if you work it out from trigonometry, I won't talk about that right now. We earlier used to call it the x component, and this one we used to call it the y component. But since you people have done trigonometry now for a couple of years, the x component will actually work out to be t cos theta. Okay, you should be familiar with this by now. So therefore, in this kind of situation, you write the work done not as t times s, but you write it as t cos theta, because the cos theta part is the one that is causing the displacement in this direction. Then you multiply it with s, and then you get the work right. Now this cos theta is an interesting thing. When theta goes from let's say 0 to 90 degrees, if you know the cos function well, then you can also see why there is full work done over here. Cos 0 will be equal to 1 and no work done over here. I beg your pardon. Work will be t times s over here, because cos theta, cos 0 is equal to 1, and no work is done over here because cos 90 degrees is equal to 0. Okay, so that ties in with our idea that no displacement takes place over here, full displacement takes place over here, because the entire amount of force is causing the displacement, and in this case only part of the force is used for creating the displacement. That variation of theta and what it does in terms of work done, we will examine in tomorrow's class.